Okay, thank you. I hope that you can hear me.
Yes.
And that's great. So good morning, good afternoon, good evening, depending on which part of the world you are. For me, it is late afternoon, and today we'll be talking about pseudopotentials or effective core potentials and their place in quantum Monte Carlo. I would like to acknowledge my current graduate students, Omar and Aksa, who already contributed to this project. And of course, as you can see, we are supported by Department of Energy, in particular by the Center for Predictive Simulation of Functional Materials. So let me go right away into, into the next view graph. Well, you might or might not know, this is a very difficult subject, so it's almost impossible to explain everything in one talk, but I'll try. And the reason is that it's very highly technical, and there are complicated constructions, which in time are not getting any more simple, but just the opposite, they are getting more complicated. You probably, if you know electronic structure codes of various types, you often find out that this is the most complicated part of those codes. Therefore, these are all sort of on the negative side. On the positive side is the following. Pseudopotentials are typical examples of well-defined, well-controllable, effective Hamiltonians, which means that you build a Hamiltonian which describes the physics of interest while eliminating the things which you are not interested in. And well, it sounds exciting, but I mean, what are the advantages? Are they really necessary? And the short answer first is the following. You gain on efficiency a lot. Over the course of about 50 years of pseudopotentials, we probably saved trillions of hours of computer time by using them. And even more fundamentally, eventually, no matter what you do, you run into very hard barriers, and it's impossible to do calculations of valence properties without using some type of effective core potentials or pseudo-potentials, whatever you call them. We'll actually come to the vocabulary in a little bit of time. So there are both efficiency reasons and fundamental reasons. So the outline of the subtopics which I will be talking about is first, sort of a rehash one-particle self-consistent methods. I hope that this is familiar to everybody here. Then we'll talk about the core versus valence, length and energy scales, dependence on the atomic number. Then we'll dive into how we describe effective ions, pseudo ions, by effective potentials in the core plus valence electrons. Then we'll talk what's the impact on QMC and why this is perhaps even more important in QMC than in many traditional methods. And then we'll talk about how it is actually realized in VMC and DMC methods, involved localizations. And I mean, involved localization approximations, T-moves, and other nitty-gritty stuff. Eventually, we'll cut it off, and Omar will then present new generations of effective core potentials, which we call correlation consistent effective core potentials, and the related topics. And eventually, while doing runs, you will run into these in one way or another. So let me go into one-particle self-consistent methods. Imagine that we want to calculate the electronic structure of an atom by one of the commonly used self-consistent one-particle methods, such as density functional theory or Hartree-Fock. I'm sure, or I at least assume that you are reasonably familiar with these types of approaches. So density functional method builds on one particle density, but in order to get a one particle density in a practical manner, you need one particle orbitals. One particle orbitals are solved in one particle Schrödinger equation, which is given in here. And of course, the components are kinetic energy, external potential, which is the bare Coulomb potential, and effective potential, which is built in the DFT theory. We'll not talk about those, but basically you calculate then the eigenvalues and eigenstates. Once you get the eigenstates, you get the density, you plug it back, and you iterate until self-consistency. Hartree-Fock goes in a very similar manner. So the wave function which you build in this case actually is a more complicated object. It's not only density, but it's a Slater determinant. And you use variational property to seek the variational minimum. And basically, you again end up with the one particle equation with one particle eigenstates and eigenvalues. And again, you calculate them, collecting all the terms in one particle Schrödinger equation. That enables you to build a new version of the effective potential of the Hartree-Fock or Dirac-Fock or Dirac potential or Fock potential, depending on which type of a method you are actually using and how deeply you treat the effects of relativity. Again, you run this in a self-consistent loop. And so eventually you end up with one particle eigenvalues and one particle orbitals. So we end up with one particle orbitals, and those could be divided into core orbitals and valence orbitals. There are fundamental differences between these two sets, and those differences goes into spatial distributions and corresponding energy scales, one particle eigenvalues. So here is a plot of one particle eigenstates multiplied by radius. So and radius times the L plus 1 power of the radius. So you get something if you take a square of these orbitals here, you would get a probability density of distribution in space of that particular state. Now you see there are essentially two types of states here. The valence states, which is 2s and 2p, which have tails going in the radius, say beyond 2, 3 bores. And then there's 1s state, which is highly localized, and it goes to 0 a little bit beyond 1 bore. Okay, and it goes exponentially fast. Therefore, it doesn't reach actually the bonding region, which is somewhere around 1.5 to about 3 Bohr radii. And obviously, you see that one state is actually not probably contributing too much to bonding properties, besides creating a repulsive barrier for the valence states. Now, this is a pretty clear sort of a distinction in space between these two types of states. This distinction becomes a little bit more complicated if we look at more complicated atoms, say like a copper, where again we have similar plot, and you see that 1s and 2s orbitals are highly localized. Then there are valence orbitals, which is 4s and 3d, which go through the bonding region, which is roughly again 1.5-ish, something to about 3.5 or so. Essentially, the chemistry doesn't move too much if you go through the periodic table. It shifts a little bit, but not too much. But now there is this strange 3s state, which is a little bit complicated. It seems that it wants to be the core, but also the tail goes into the bonding region. It's not large, but it's not negligible either. We could call these semi-core states. And if you want to reproduce the valence properties with sufficiently high accuracy, you need to include them in the valence space. So you end up with a little bit more electrons, but you describe the valence effects much, much more accurately. We'll come back to, sort of bargains which you can get using various sizes of the cores later. Now, What happens if you put these atoms into the bonds? For example, carbon-2 dimer. On the left side, we have core orbitals, molecular orbitals, but they look like atomic orbitals. These are isosurfaces of the squares of, isosurfaces of the, not of the squares, but of the molecular orbitals. And here is the bonding. Therefore, both of them are positive. And you see these are small spherical surfaces, very closely localized to the around the nuclei. So that basically gives you the position of the nuclei. This is the anti-bonding, and again, they are just spherical because it's anti-bonding. One is positive, yellow, the other is negative, blue, but otherwise they are localized and they don't contribute, they don't overlap from different atoms. They are essentially lost in there in the core, very close to the nuclei. You see on the right side, we have the valence orbitals. They, of course, are not spherical. They change the shape, and you see the positive lobes and negative lobes, yellow and blue. You see pi bonds here. Here, sigma bonds from s orbitals and sigma bonds from pi orbitals in the z direction, assuming that the atoms are lying on the z-axis. Obviously, the atomic orbitals didn't change from the core orbitals didn't change from the atomic orbitals at all. They essentially remain the same. The valence orbitals change very dramatically and describe the chemistry of the system. Now, so that basically concludes the the spatial characteristics of the core states versus valence states. Now, there is even more important point, especially for quantum Monte Carlo methods, which works with the total energies, and that's the dependence of the energies or eigenvalues of one particle states on the nuclear charge. Obviously, the core states are more or less hydrogen-like. Therefore, the eigenvalue is essentially z squared divided by n square, where n, if n is the principal quantum number, therefore for 1s it is equal to 1. And then the core states can span several orders of magnitude, starting from about 100 to about 10 to the 6 or higher, beyond, even beyond million, if you go to sufficiently heavy atoms. And therefore, these energy scales are such that the atom is that state is so closely localized to the ion that it doesn't enter into any chemical bonds. It doesn't affect the chemical properties, besides creating a repulsive barrier. That repulsive barrier, of course, is special for each atom, and it does affect the chemical properties. So we'll have to build that barrier in a very particular way. Now, there are these semi-core states, as I mentioned, for the copper atom, and they occupy sort of a range of energies between 30 and 100 electron volts. And sort of it complicated our lives, but we have to learn how to live with those. And very often we have to include them explicitly into the calculations, like the valence states, which are between, 1,000 of an electron volt, like Rydberg states, up to about 30 electron volts, which are sort of close to the semi-core level of energies. So now, why I'm mentioning this? Well, as you already have probably learned, crucial for efficiency of the quantum Monte Carlo, which is a total energy method, is the fluctuations of the local energies, which you encounter in sampling the wave functions, or any types of expectations which you can think of, since they are weighted by psi square. And in DMC, it is not only psi square, but psi square times the expectation value of the energy in the exponential. And those fluctuations to the first order, they really scale like z to the fourth, namely square of the energy, obviously. So efficiency of sampling of the valence energies and bond energies, gaps and values which are all the order of 1 to 5 to 10 electron volts would be very low if Z gets very large. So for example, for helium atom, this is not a problem because the sigma square is small. But for copper atom, sigma square is already 100 in atomic units. So you would actually try to seek a signal on a fifth decimal, in heavier atoms on a sixth decimal, in even heavier atoms on seventh decimal. So there is a slowdown just between helium and copper by a factor of 500. For heavier atoms than copper, it is essentially impossible to use. Or you have to adjust the method and calculate only a single atom. So while we are interested in valence properties, almost all the time would be spent on sampling irrelevant degrees of freedom and irrelevant fluctuations which belong to the core. Obviously, we want to do the following. We want to partition electronic structure of the atoms into two pieces. Core states, which are rigid, they affect the valence electronic structure, but that particular influence is first of all very small, and it can be mimicked extremely accurately. Therefore, we build on the partitioning because of different energies and different length scales. So we want to eliminate the core states or electrons and keep only the valence part. Well, you say, well, if the core electrons only repulse the valence electrons, we need to build some repulsive effective operator, except that it cannot be a simple effective potential, but it must be angular momentum dependent potential because of different number of core states which are occupied in particular channels. Say whether this is core which is only 1s2, or it's a core 1s2, 2s2, 2p2, or 2p6, or so. Therefore, it has to be angular momentum dependent. So we build the so-called effective core potential operator or pseudopotential operator, which is the following form. And it is the projectors on the angular momentum states, potential functions in the front. You sum over the lowest angular momentum channels. For example, L can be 0, 1, 2, or so, namely S, P, D, and so on, until you capture enough channels to represent the atom correctly, and then you have effective local potential. Okay, we'll repeat that here, and here comes also a little bit of a dictionary. So in condensate matter physics, historically, these objects are called pseudopotentials. In quantum chemistry, because of also historical reasons, these are called effective core potentials. There are minor and sometimes more major differences, since there are about 20 or 30 types of possible constructions which have been used over the last, say, 50 years. It goes back to the 50s, 1952 or 53, when the first papers appeared that this construction would be useful, and from that time it has been developing ever since. Now, in the pseudopotential W operator, as I said, there are projectors on the angular momentum states of the atom, and there are radial pseudopotential functions for each given symmetry channel. There is a local potential which qualitatively behaves like effective charge of the ion or pseudo ion divided by R, so it's an effective Coulomb potential outside the core. There is this projector operator, and as I mentioned, L is summed up to some number of different occupied channels, and it can be 1, 2, 3, or 4 for the heaviest atoms. So we say that these objects, these operators, are actually non-local. What does it mean? Basically, S electrons will feel different potential than the P electron will feel. Here is kind of a qualitatively now for all types of pseudopotentials which are bounded in the origin. This is how they look like. Obviously, for carbon, we have a 1s2 core. Therefore, the S pseudopotential is repulsive, and it is more repulsive than P pseudopotential because in P channel there is no P electron inside the core. Outside the core, beyond say 1 Bohr, you see they go into Z effective divided by R, namely -4 divided by R in atomic units. In this case, since we have a carbon and there are 4 valence electrons, 2s2 and 2p2. I guess that you all know this. Obviously, this non-locality would come back if we recall the self-consistent loop for one-particle eigenfunctions, where the pseudopotentials were actually first, conceived and constructed. The external or bare ionic potential is replaced by the pseudopotential, and in S channel it looks like this. That there is this S function which is repulsive, and in P channel this is more attractive, although not as attractive as usually, because even P electrons feel a little bit of S electrons, and therefore it just goes to a finite value or into some value depending on the type of a construction. In this case, it is simple because it goes just to a finite value like we saw in the previous plot. Good. Now, how to use these interesting objects which are non-local? What does it mean if we try to build a matrix element of this W operator? As here, we put R on one side, R prime on the other side, and it gets off-diagonal matrix elements which are not zero. Remember, if W would be on local potential, it will be local, namely, it will be non-zero only if R would be equal to R prime. Now, in this case, it will be more complicated because the W's will depend on electron and ion, and we will sum over all electrons and ions over these matrix elements and apply these to our trial or variational wave function and do this interesting integral, okay? Now, this integral, of course, so non-locality means we have to integrate because there are off-diagonal matrix elements. Now, it gets kind of a long thing. The projection operators actually in the atomic case are spherical harmonics, and over those you need actually to calculate. Therefore, we'll be integrating over the spherical surfaces for a given fixed value of the radius of the electron around the atom. And we have to calculate over all the channels which are included, and this is done numerically because the objects, our trial wave functions, could be very, very complicated. These are genuine many-body objects. Therefore, we want a completely general scheme. The only way how to do it is actually to do a numerical integral. This is done, you get special quadratures which are particularly accurate for spherical surfaces, and therefore you just calculate the value of the wave function over the surface of the sphere, and then you just multiply by this potential function, and basically you have the action of the pseudopotential on the wave function. So in variational Monte Carlo, this is just a matter of numerical work, which is straightforward. It's long, it's costs quite a bit because for each position of electrons, you have to do really this spherical integral, but nevertheless, it can be done more or less straightforwardly. Okay. Now, the question is, what is the gain? Even if we look only within the variational Monte Carlo. And this is an interesting table. We'll take iron atom as an example, and we'll do variational calculations for iron atom with all electron occupation, iron atom with core, which would be neon core, namely that the occupation will be, you remember for copper case with 3s electrons and 3p electrons, in semicore, but we'll treat them as valence, and therefore we have all of these electrons from subshell 3 occupied. And then we'll try to simplify even more. I'll say forget about the semicore electrons, let's put them in the core, and we will have only D and S states. And obviously here 3D2 is incorrect. There should be 3D6 as it is here, but it's a minor typo. And now let's have a look on these, on these rows here. So Hartree-Fock energies are given in here for these three cases. You see, energy goes down by an order of magnitude as you go from one column to another. Variational energies, of course, follow because you just add the correlation. They are very similar qualitatively. Now, we look at the variance, and in one case, the variance is about 50 in atomic units. It's about 1.5 for the neon core, and it's about 0.16 here. As I promised, they go down by 2 orders of magnitude. The energies goes by 1 order of magnitude. And indeed, then if you look at the efficiency, which is given by 1 over the sigma squared times the decorrelation time, that's just a minor modification, you essentially get 2 orders of magnitude jumps between these. Now, obviously, the argon core looks great because the efficiency went up by 4 orders of magnitude. Trouble is, if you check the accuracy of the valence properties, they are not very good. And they essentially start to reach errors which you see in DFT or other methods. Therefore, that is not the optimal choice. And the optimal choice is actually neon core, where the errors are less than 1/10 of an electron volt nominally. And there are still some residual errors, but it's under your control. You can always improve the effective Hamiltonian doing more refined constructions. But that's not a subject in here. But here I put the valence errors in the all-electron atom in quotes 0. They are not completely 0 because there are relativistic effects. In particular, in iron, of course, dominate the scalar, the more simpler relativistic effects, and we could easily build them into the pseudopotentials. So actually, this would have similar systematic errors if you would not include the scalar relativistic effects into all electron calculations. So in fact, if you would use just without thinking the pseudopotentials, you would be more accurate than using without thinking all electron calculations, because the scalar relativistic effects start to show up, and they are also of the order of about 0.1 electron volt for the energy differences. Now, that looks great. So we know how to build the CPs. We know what is the size of the core we should choose in order to guarantee the accuracy which we want. Now, the trouble is, if we want to use this thing in the diffusion Monte Carlo method, because in the diffusion Monte Carlo method, we have another problem, which you probably heard about, which is the fermion sign problem, namely the evolution of the sampling point, Walker's quantum, QMC samples, has to be such that it never crosses the node of the trial or variational wave function. But the localization approximation, but the non-local pseudopotentials go exactly against this, because there are non-local moves, because the electron can move and it would have a non-zero probability to go there, because the non-local operator has non-zero matrix elements there. It's not like a local operator which acts only at the given point. So that could easily violate the fixed node condition. So about 33 years ago, we and other people and us introduced the so-called localization approximation by using a projection on an accurate trial wave function. Basically, we evaluate the action of the non-local operator on the trial wave function, and we divide by the trial wave function. So this is a complicated projection on the trial wave function. The resulting operator is very complicated, but you never see it, you just evaluate it. Now, what are its properties? So the bias which you generate using this transformation is quadratic in trial wave function error. It means it converges quickly, and it converges like the other components of the energy. So it is so-called, it has zero variance property. As trial wave function moves towards the exact ones, the biases decrease quadratically fast. The trouble is that it generates a new effective potential, which is can be wild in principle. It is not in practice, but in principle it could be wild. So the energy would not be necessarily an upper bound. The point is that if you try this in practice, it generates small biases which tend to cancel out in difference. In fact, most of these errors from this transformation are often buried in fixed node biases. This is not always true, but mostly true. Fortunately, we have also an alternative, which is called T-moves. And this is even a little bit more complicated. So you divide the moves of the quantum Monte Carlo walkers or sampling points into two categories. One which violates the sign problem, the other which doesn't violate the sign problem. The fixed node approximation treatment of the sign problem. So if the move keeps the same sign, you actually use a sample, not an average projection as in the localization approximation. Otherwise, if it violates the sign or generates a sign flip, you use the weight exactly like the localization approximation. The key point is that it restores the total energy upper bound property. On the other hand, it introduces no zero variance property, so there might be some increase in computational effort. In practice, it turns out that this increase in computational effort is not very large, and this is now the preferred method to use because it keeps the total energy upper bound, which is much stronger than the zero variance. But fundamentally, these two methods are complementary. What works in one doesn't work completely in the other, and vice versa. Now, let me mention the pseudopotentials and effective core potential advantages. And as I alluded to in before, there are both fundamental and technical reasons. So number one is the very big decrease in energy fluctuations, which is crucial for the efficiency. Everything what we do in the diffusion Monte Carlo actually depends on the fluctuations which you encounter. Now, fundamentally, ECPs of some type are unavoidable for larger Z. If you have multiple heavy cores in a system where you want to calculate, say, a large molecule piece of a solid surface, it is guaranteed that you will not be able to properly correlate the heavy cores within the relativistic framework which you need for a larger system. It's impossible, period. So one has to use, if you want to calculate a larger system, some type of pseudopotentials or effective core potentials are necessary. Now, technically, which is also important actually, because sometimes if you just say, well, if I had 100 times bigger computer, I could do it, but simply you use smaller and smoother bases, regardless whether these are Gaussians or plane waves, it applies to both. So typically you save a lot on the basis sets to build the one particle orbitals and slated determinants and the rest. You reduce the number of degrees of freedom, which is pretty significant if you think about the fifth row. And essentially, you have a very finite number of degrees of freedom throughout the whole periodic table while the Z is growing. And last but not least, scalar and also spin orbit relativity effects on valence space is possible to include in a straightforward manner using two-component spinners and so on, so they could be actually folded into these pseudo-potentials or effective core potentials formalism. Now, there's a vast amount of literature on pseudo-potentials. My suggestion would be don't read those at the first thing, because you might be buried for a long time into the whole thing. If you want to understand actually non-local ECPs and quantum Monte Carlo, I would suggest our paper from '91, which is reasonable theory, reasonable amount of technical information, and it's pretty complete on a localization approximation. Timu's paper by Kasula is also fairly exhaustive. Essentially, you find out how to do that in a very accessible manner. And then relativity and spin orbit, Cody's papers from 2017 and 2016 basically cover everything what you need to know about the whole thing. Of course, the more refined things, you can look at other papers, but basically this should be a good start. So this is not that many papers to study. Okay, the last thing I want to mention, that would be our project on correlation consistent effective core potentials, which was the project which we started now about 8 or 9 years ago, which was built on sort of a desire to put the things a little bit under the control, to design ECPs or pseudo-potentials which would be easy to use, which would be well tested, and fundamentally, which would correspond to the many-body physics and many-body methods to be used, namely that they would actually very precisely reproduce also correlated properties, not only one particle based things. So the fundamental point is that we are using traditional constructions, most of them used one particle eigenvalues and one particle orbitals and related properties as a guiding principle to reproduce the properties of atom, and by sort of pushing it into larger systems, valence properties of molecules and solids. So in this project, we actually explicitly said we will do many-body constructions. Namely, we actually calculate total many-body energies, namely many-body eigenvalues, and there are differences like ionization potentials, electron affinities, excitations, and so on. And we look at true many-body binding properties, say like molecular binding curves, and later on, by essentially using it in various calculations, we verify that they also work in other chemical environments like solid surfaces and so on. There are also other improvements, both in fundamental accuracy and in practice, because we expanded that to spin orbit effects and so on. But here I'm actually trying to still keep enough of a time for Omar's talk, where he would be talking about the specific of these correlation consistent effective core potentials, as we call them. And we hope that you will find them interesting and then you will use them. We see increasing rate of use by the community, but because they realize that actually we are trying to build a qualitatively a different version of the whole thing, where we build on many-body properties instead of one particle, or combination of one particle properties and many-body properties, which are typical for previous constructions. So I think that this is a good time for me to stop. I'll try to stop sharing, and I'll ask Omar to share his talk and tell you about the specifics of this project.